Myself, Kantraj, Assistant Professor of Physics, Government First Aid College, Malur. So this is the class for BSc Physics, third semester, Bangalore University North. And the title of this paper is Electricity and Magnetism for the paper 301. So today's session is to solve the problems in network theorem. So when you see about the learning objectives of this topic, solving the problems in superposition and maximum power transfer theorem and calculate the different current and voltages in the given networks. And also to calculate the maximum power transfer through the load or power dissipation through the load. So let us take an example. So using the superposition theorem, determine the voltage drop across 3.3 kilo ohms as shown in the figure below. So when you circuit, if you see the circuit here, two voltage sources will be there, 8 volts and 5 volts, and three resistors, one is 2 kilo ohms, 4.7 kilo ohms and 3.3 kilo ohms. So we have a statement for superposition theorem, like any linear bilateral network having more than one sources, the response of across any element is sum of the responses obtained from each sources separately. So that statement, when you see a number of sources which is connected, either voltage source or current sources, we can apply the superposition theorem by taking certain steps for that. So basically when you explain the superposition theorem, so the step 1 we are going to calculate the effective value of resistance or the voltages. So first you want to select one source in the circuit and replace all the voltage sources by short circuit and all current sources in the open circuit. So we don't have any current source. Let us take, we have only voltage sources. Now what I am going to do here, first thing, remove the 8 volts power supply from the original circuit and new circuit will become, and then measures the voltage across the resistors. So when you removing the 8 volts source, see that it should be shorted, ideal voltage should by short circuit, and the 5 volts is acting alone. So once if we have 5 volt source for the circuit, I want to calculate what is the resultant resistance will be for the circuit. So 2 ohms is parallel, 2 kilo ohms is parallel with 3.3 kilo ohms in the circuit. So 2 kilo ohms into 3.3 divided by 2 kilo ohms plus 3.3k, which gives one effective value. That effective value is nothing but 1.245 kilo ohms. This is one equivalent resistance for the combination. Now simplify the circuit, and by seeing a simple circuit, we have a two resistance, one voltage source. So what is the voltage across the terminal 1.245 kilo ohms I want to calculate. So looking back to the circuit, when you remember about your voltage divider rule, so we can apply the voltage divider rule. What is that voltage divider rule? Says that the total voltage into the value of that resistance divided by the sum of the resistance, that is what is called as voltage divider rule. So similarly, when you are applying for this circuit, the total voltage is 5 and the particular value is nothing but 1.245 kilo ohms, and the sum of the resistance is nothing but 1.245 plus 4.7 kilo, that gives about your value 1.047. Similarly, the step 2, remove another source and short the terminals and keep another source will be acting. So now remove the 5 volts and short the terminals and keeping the 8 volts will be alone. So now again I can repeat the same thing. 4.7 and 3.3 kilo ohms will be a parallel combination. The parallel combination shows the effective value 1.938. So again I can apply the voltage divider rule. Since the voltage divider rule says that the total voltage is 8 into 1.938 divided by the sum of the resistance is 1.938 plus 2 kilo, this gives about the value 3.9337 volts. Therefore, the voltage drop across the 3.3 key resistor is V1 plus V2, which is equal to 1.047 plus 3.937, so is equal to 4.9847 volts. So this is way to calculate the voltage drop across the 3.3 kilo ohms for the original circuit according to the definition. When you want to calculate the response of any element is nothing but sum of the responses obtained from each sources considered separately. So this is what we are going to prove the superposition theorem. So let me see another example. When you want to discuss about the currents, so this is an example for discussing the currents using the superposition theorem. So determine the current through the 10 ohm resistors as shown in the figure. So looking the circuit, we have two voltage sources. One is 15 volts and other one is 13 volts. The resistors like R1 and R2, R3, we have a different resistors. So as a step 1, I told that select any one source and replace all the voltage sources by short circuit. If it is having a current sources, you can replace by open circuit. Now we don't have any current source in the circuit, just replace all the voltage sources, or if you have one voltage source, we can keep it as one voltage source remaining, you can short the circuit. So V1 keeping alone and V2 is shorted, so V1 is equal to 15 volts and that value of effective value of your circuit, because I want to concentrate on the current. So I want to calculate the current in the given network, means first I want to calculate what is the total effective value of the resistance of the circuit. So once if you see the combination 20 ohms and 10 ohms, it is a parallel combination. The 20 into 10 divided by 20 plus 10 will get it as 6.7 ohms. That 6.7 ohms is series with the 100 ohms. So finally we'll get R equivalent is equal to 106, that is another 6.7 ohms. So once if we get the total resistance of the circuit, finally we get IT is equal to, that is total current is equal to V1 divided by R equivalent. So R equivalent is already we know, and V1 is already 15 volts. If we substitute it here, we get that 0.14 amperes of current flowing on the total current in the given network. So once if we calculate the total current, but I want to calculate what is the current flowing on R3 with an individual source. So I can use one of the method is called current divider rule. The current divider rule says that for any circuit, if you want to calculate the branch current for devices or elements, we can find out a particular branch, particular value of resistance. So that I is equal to, or some value, I is equal to I1 or I2 something, I1, I2 or whatever the value we are chosen. So I1 is equal to total current into the particular, that another branch of the resistance divided by the sum of the resistance, that is actually the current divider rule. Now I can same thing I am going to adopt here. IR3 means the current flowing on R3 is equal to the total current is 0.14 ampere into the value of other branch is 20 ohms divided by sum of the resistance 20 plus 10, which is nothing but 0.094 amperes. This is the current flowing on the R3. The similar way we can explain that the source V2 is alone and V1 is shorted. That is V2 is 13 volts I told, and V1 is 15 volts. Just I am going to replace the 15 volts by short circuit and keeping the alone, that is keeping the V2 is acting now. So similarly I can calculate the value of resistance, that is equivalent value of resistance R equivalent. Again I am repeating, R equivalent is nothing but the combination what is this and that series with the resistance. The total value of the resistance for the circuit is called as R equivalent. So the 110 divided by 100 plus 10, 100 into 10 divided by 100 plus 10, you will get some value. That value you are going to add the 20 ohms, so we get it as R equivalent. That R equivalent is equal to 29.09 ohms is the effective value of the or equivalent value of this network. So once if we know equivalent value, IT you can calculate. IT is equal to V divided by R equivalent, as I calculated previous one. So we get it as 0.047 amperes. The similar way, IR3 is equal to 0.406 ampere. So how to get the 0.046 ampere means, again I can apply the branch current method. The total current of the circuit is nothing but 0.047 into the value of another branch. Now I am looking from here. So the current is from like this. So this is nothing but the total current IT is 0.047. So if I want to calculate IR3, so the total current into the another branch of resistance divided by the sum of the resistance gives about IR3 0.406 ampere. So like the way which you can calculate the currents with the different individual sources acting alone. So I can use the total circuit here, the current flowing on first one 10 volts, what you will get, the current flowing on second one 0.46. If I mark the direction like this, you just added the two sources. So adding the currents here, that is IR3 is equal to 0.5 amperes, you will get the current across the 10 ohm resistor. So this is the way to calculate the superposition theorem with current sources, with the voltage sources, and that I want to calculate the branch currents in a different points. That is the superposition theorem. So take the one more example. Using the superposition theorem, find the current, find in the circuit figure. Superposition theorem to find the voltage or current, whatever you want. So let us take that this is the combination of circuit. The combination of circuit implies that one is voltage source and one is current source. So I want to calculate what is the voltage. V is equal to V1 plus V2. If it is having a branch like first loop as V1 and second is nothing but V2, the total value is nothing but V1 plus V2. Okay. So or the voltage drop across is nothing but V1 plus V2. So looking back to the previous sums, when I want to use any method, if you have any voltage sources, you short that, and current sources open. That steps you can follow here. So first I want to keep the 6 volts supply as it is, and remove the current source because this is the current sources. So I can open the current source, so I can calculate the current across this or voltage. So when you see about the 6 volts is taking one circuit, what is the voltage drop across 4 ohms means? So simple voltage divider rule we can follow here. That is 6 volts. The 6 volts into 4 ohms divided by 8 plus 4 gives about the voltage, that is 2 volts. So when you want to calculate the second step, so taking the voltage source will be short circuit, that is V1, and take only the another source, that is current source. We have 3 amperes of current. So I can calculate what is the voltage drop across the 4 ohm resistance. So when we have a current source, so no need to calculate any equivalent or what else the voltage, everything. So directly you can use it, the current divider rule, because the total current in this loop or a mesh is 3 ampere. So I3 and I2 is nothing but indicating the current with the 3 amperes. So what is the current flowing on the 4 ohm resistance? It is I3. So once if we know I3 from the branch current method, the branch current method says that the value of another branch into the total current into another value of the volt resistance divided by the sum of the resistance, we will get it as 2 amperes of current flowing across the 4 ohms. So from the Ohm's law, V is equal to I into R. So what is V2? V2 is equal to 4 into I3. So 4 into 2, which is 8 volts. So adding the two voltage sources, V1 is equal to 2 and V2 is equal to 8 volts. So we get that V is equal to 10 volts. Like this, we can take any type of superposition theorem and you can solve the different branch currents, or it may be a branch currents, voltages. So the sum of the voltage, everything in the superposition theorem. Now let us take an example. 4. Find the value of load resistance, that is RL, for the maximum power transfer in the circuit and find the maximum power. So this is a circuit which I am going to calculate by using the maximum power transfer theorem. So when you have such type of circuits, the process of making the load resistance is equal to the Thevenin's resistance, all these things, whichever we can see in your maximum power transfer is for load matching circuits. So I can state the maximum power transfer theorem from any source, that is the maximum power is transferred from a source to the load. The load resistance is equal to the internal resistance of the source or Thevenin's resistance. That means when you want to calculate the load resistance of the circuit, so the maximum power is transferred from the source to the load when the load resistance is equal to the Thevenin's resistance. What is the statement of your maximum power transfer theorem? So let us take an example for this one and calculate the important things. Like first I want to calculate what is RTH and what is the VTH value. After that I can calculate the power delivery to the load. So step number 1, when you see about the circuits, it consists of 30 volts and different values of resistance R1, R2, R3 and R4. Between the points like A and B, we are going to have one load resistance that I should calculate what is the load resistance, and then you can calculate the power maximum. So the step number 1, disconnect the load resistance from the load terminals A and B. So when you have a circuit like this, so I want to disconnect the load. Disconnect the load means if it is A and B as the load terminals, so I should disconnect the load, and to represent the given circuit, the Thevenin's equivalent, we can determine the variables like what is VTH and what is RTH. So let us calculate, the first thing is nothing but VTH value, that is VAB, the open circuit voltage. So the open circuit voltage is nothing but VAB. The VAB is nothing but VA minus of VB. So what is the VA and what is VB means you can calculate separately from the voltage divider rule. So as I said that voltage divider rules is very easy to calculate the voltage across the different point. Suppose the 30 volts is flowing to the resistance either R1 or R2 and it's parallelly connected, the same voltage will be flow across R3 and R4. So I can apply directly the voltage divider rule for the points A and B. Let us take an example first. VA. VA is equal to V into R2 divided by R1 plus R2 is the formula for voltage divider rule. Substitute the values of V, 30 volts, R2 is 20 divided by 20 plus 15, we'll get it as 17.14 volts across the point VA. Similarly, we can calculate VB. The VB is nothing but this is the point VB, and VB is equal to V into R4 because the lower thing, it's R4. V into R4 divided by R3 plus R4, that is the combination of this circuit. So applying the voltage divider rule for this. So 30 volts, R4 is 5 ohms divided by 10 plus 5, we'll get as 10 volts. So VAB is equal to VA minus of VB, 17.14 minus of 10, we'll get as 7.14 volts. This is what is called the voltage across the point VAB, that is VTH. Similarly, you can calculate the Thevenin's equivalent circuit. So considering the Thevenin's equivalent circuit, again applying the same steps, calculate Thevenin's equivalent resistance RTH by replacing the sources of the internal resistance. So and see if it is having any voltage source. You just short the remove the voltage source and short it the terminals and calculate the effective value of your where it is marked on the load resistance. So that is called RTH. So Thevenin's equivalent resistance is across the terminals A and B. You can calculate RTH. So when you look about the circuit, if I am going to have a folding like this, these two resistors will become parallel combination, and the same effective, it will become a combination of your R3 and R4 is parallel, and R1 is R2 is said to be parallel. So that effective value will be calculated across the A and B. So what is RTH? RTH is equal to RAB. RAB is equal to the combination of two parallel combinations are connected in the series thing. So I can use it as R1 R2 divided by R1 plus R2, one effective value of R1 and R2, and R3 R4 divided by R3 plus R4, another effective value of the combination. These two combinations are connected. I can calculate a series so that I'll get it as 8.57 plus 3.3 ohms. We'll get it as RTH. RTH is equal to 11.9 ohms as the total resistance on the given network. This is what is called a load resistance or RTH. When you see about your step number 3, finally we can replace back all the voltage sources and all the Thevenin's resistance. So with the equivalent circuit, that is what is called VTH series with the Thevenin's resistance and connecting back to the load. So then it will become a Thevenin's equivalent circuit. The step 3, the Thevenin's equivalent circuit with the above calculated values by reconnecting the load resistance as shown in the below. From the maximum power transfer theorem, RL value must equal to the RTH to deliver the maximum load power to the load. That is actually we know from the definition. So RL is equal to RTH. It is 11.90 ohms that you can add it here. So about the maximum power transferred under the condition P maximum is equal to VTH square divided by 4 times of RTH. Substituting the value here, square is written like underscore. So this better you can 7.14 square divided by 4 into 11.90. That gives about the value. It is 1.07 watts. This is the power delivered to the load. 1.07 watts will be the answer for the question. So like this we can solve the maximum power transfer theorem. Let us take one more example for this. Find the value of RL for the given network below. That maximum power is maximum. And also find the maximum power through the load resistance RL by using the maximum power transfer theorem. So looking to the circuit, we have one voltage source 6 volts and different resistors 6 ohms and 8 ohms, 5 ohms and 12 ohms, and the load is not given, so I should calculate. The first step is nothing but load RL is disconnected from the terminal C and B. Corresponding diagram we can write it here. If we disconnect the load resistance, so the circuit will be reduces like this, and see that I can calculate the voltage or what is called as the load resistance first or RTH. So the effective value, this combination, if I am going to remove the value of 6 ohms, that is procedure, 6 volts battery is going to remove. 6 into 8 divided by 6 plus 8 will get the effective value, that is 3.43, and 5 ohms and 12 ohms as it is. So the combination of 5 ohms with 3.43 and 12 ohms, it is like just 3.43 is series with the 12 ohms, and that is combination with parallel for 5 ohms. So looking here, 15.43 is adding by 12 and 3.43 will get 15.43 ohms, and this combination is again a parallel. So finally we will get 3.77 ohms for the resistance, that is RAB or RL or RTH, 3.77 ohms. So now I can calculate the VTH value. So calculating the VTH value for the given network. So replacing back to the first similar circuit, same circuit, and only the terminal C and B I opened here. So looking back to the given network, so I can use any methods, but let us see for mesh analysis method also to easy to calculate about the voltage across the point, what is the voltage drop across the 5 ohms I want to calculate. So when you want to calculate the voltage drop across 5 ohms, because when you have only one source and see the combination of resistance will be there, just apply the KVL for the loops. So the loop first I can apply, so 6 minus of 6I1 and 8I1, so the current is moving in opposite direction, minus of 8I2 is equal to 0. So this is 14I1 plus 8I2 is equal to minus of 6. This is what is called the first loop network equation 1. Again applying the KVL in the loop 2. So loop 2 will be, we don't have any source here, only the current flowing across 8 ohms is 2 currents, I1 and I2, and the current flowing on 5 ohms is 1, and 12 ohms is I2. So substitute the value, or substituting this one, that is 8I2 minus 5I2 minus 12I2 plus 8I1 is equal to 0 for this network, KVL, and simplifying this 8I1 and minus 8 minus 5 minus 12 minus 25I2 is equal to 0. That is equation 2. Solving the equation 1 and equation 2, so we get I1 is equal to 0.524 amperes and I2 is equal to 0.16 amperes, 7 amperes. So now from the circuit, VOC is VA minus of 5I2 minus of VB. So this point is the total value of open circuit voltage. I can read it as, so VAB is equal to 5I2. So this is open circuit voltage. So VAB is nothing but VOC. So 5 times of I2 gives the voltage across the VAB. So that is 5 into 0.167, we will get it as 0.835 volts. That is what is called a Thevenin's voltage or open circuit voltage. So the maximum power through RL is given by P maximum is equal to VOC square, that is VTH square, divided by 4 times of RL. So what is VTH square or V open circuit voltage means? Substitute the value of VOC. So 0.835 whole square divided by 4 into, that is RL is 3.77 ohms. Substituting we will get 0.046 watts. So like this we can say that 0.046 watts of power will be delivered to the load resistance. So this is how we can calculate the maximum power transfer theorem. We have simple circuits in your book. You just try it out, because a network which is having complicated, I have taken to solve this type of networks. So let us have a glance on that, and this is what we are going to solve the problems. The session summary is solving the problems of superposition and maximum power transfer theorems. Students can be able to understand to solve the different branch currents and voltages in the networks, and also power delivery to the load from maximum power transfer theorems. So thank you, and we are referred so many books with the reference of Omkar publications. So with Basavaraj and Sadashiv, and even Sunstar will be having both the authors, H.C. Manjunath, Dr. Vidya, and Dr. Jaishilan, Dr. Wazir Sultana, and also some of the internet sources we are referred to solve the problems. So thank you one and all for this session.